What we're going to do for the rest of the semester will be applications of what we've already learned. We'll use a version of F equals ma, energy conservation, or momentum conservation, and explore different situations where we can apply that. And the first case that we're going to look at is rotation. And where we began the semester, if you remember way back to the beginning of the semester, is that we began with rotation. We're going to do kinematics. We're going to do rotation's form of forces and energy and momentum. And so we're going to do all of these, and they're going to have similar expressions. It just turns out that it's mostly going to be in Greek, because we're going to use Greek letters for rotation. And you're used to this with angles. It feels natural with angles, but with everything else, you're like, oh my gosh. But much of this is the same that we've done before. It's just, it's all in Greek. But you can handle it. It's going to be okay. So we're going to start with kinematics. And in particular, going to define our variables. So our variables, when we think about something around in a circle, so we're really going to start with something that goes around where the axis is fixed. So a stationary bicycle wheel, a clock hand, something like that. So that's supposed to be a circle, where we'll go ahead and do sort of the normal thing, which is to say, let's say we go from here to some point here. So we go through an angle like this of theta, right? And that angle, we can compare that angle to how far we go along the outside, this arc length. Well, we know if we go all the way around the circle, then the arc length becomes a circumference. So if we go all the way around, then that means the circumference is equal to 2 pi times r. That's how far we've gone. And the angle that we've gone through, angle, is 2 pi radians. So the first thing that this tells us is that radians are natural units for rotational motion. Radians are the units we use. This doesn't mean you need to change your calculator into radians, because when you're doing sines and cosines, often you'll still have a degree that you can use to plug in. But we're going to be, if we go halfway around the circle, the angle that we use is not 180, it's pi, right, to figure out our distance. So if instead of going all the way around, we go halfway around, then the distance that we go is obviously going to be pi times r. So if we go some fraction on our arc length, this distance s is just r theta times our r, right? Instead of 2 pi, theta times our r. So that's our arc length, is theta times r. So I'm going to write it down here. S is equal to r times theta, or theta times r, where this is in radians. Okay, that's just a reminder that you need to keep it in radians so that when we have meters here, we'll get meters out here. So the radians don't really show up when we calculate this S, the length, the distance that you go around. You don't suddenly say radian meters as the answer. All right, so that's our angle measurement. And not surprisingly, we can say, well, if this changes in time, if our R is fixed, okay, so as it is for a wheel or something like that, then we say ds with respect to time is going to, well, r is going to be a constant, so we'll have r d theta dt. And so this is going to be our speed is equal to r d theta dt is omega. Okay, so that this is lowercase Greek letter omega. If you end up calling it W, that's okay, but I'm going to call it omega, and I don't want you to be confused by that. Okay, so omega is our angular speed. And because I have radians here and time here, it's going to have units. The units of omega are radians per second. Okay, so that's our angular speed. And that gives us back this speed as in meters per second. Now, typically what we're going to want though is, we know v is a velocity vector, so let's look at this. It changes, oh man, that's a bad circle. So if we look at a point here and we're going around a circle like this, then I've got this is my v here, and then sometime later the v is changing directions, which we know means that there has to be an acceleration. And this is my r. That's my distance from the point of rotation. So r is my distance vector from the point of rotation to whatever we're looking at that's rotating. And the question is, how do we describe this this angular velocity? So this rotation, right? So this is the direction that omega is going. It's rotating around like this. So we could describe it with a curling kind of thing. We could say, hey, that is not clockwise, because clockwise would be going the other way. We could say that's counterclockwise. Counterclockwise might be a direction that we could describe it as, right? Or we could call it as positive negative. We could say, and your book uses this convention, we could say that this direction, going from this point here to here on this original top drawing, that's the positive angle, because that's the normal way we measure our angle, so that would be a positive direction. So going down the other way would be negative. So another convention is to say, like, going this direction is positive and going this direction is negative, and that makes some sense. But there can be some confusion, particularly if we're looking at something and we're looking at it from the top, like a merry-go-round or a lazy Susan or something like that. So I want to point out that even clockwise and counterclockwise have some difficulties. Okay, so this is my makeshift clock. I hope you can see it. And so you can see that if I take this, this is going to be the direction, right? This hand moves. That would be clockwise. So I'm going to draw that on here. So on this, we can agree that that is clockwise, right? And similarly, I'm just going to draw it down here for a circle. Ooh, that's a terrible circle. Like this. That's clockwise, okay? You guys can see that. That is clockwise. Okay, so now you can see that this is clockwise up here, right? Right over here. The problem is, I don't see it as clockwise. I'm behind the screen right here. And if I turn this around, I can show you what I see. Now, it's a little hard because it looks like it's clockwise. We can read numbers backwards and things like that. But if we look at the down below, I think you can agree, I hope, depending on the reflections here, that this arrow that I've drawn is actually showing, if you look at it now, that looks like it's going counterclockwise. No clock goes in that direction. And that's because you're seeing it from the other side, because I flipped it. So if I flip it like this, that looks like clockwise to you, that bottom circle. And if I flip it like this, it doesn't look like clockwise. It looks like counterclockwise. So clockwise only works if we can agree which side we're looking at, that we're all looking at it from the same side. So we need another way to notate this. So this is the way that we describe it, and we use yet another right-hand rule. So this right-hand rule is what I call the curling right-hand rule. And in this case, you take your fingers and you curl in the direction that that the rotation is happening. And so in my little sort of circle here, if I look at this and I take my right hand in the direction that things are going, well, that's not the right way. I'm going to come behind and I'll go like this, and that tells me it's pointing away from the screen. But that's going to be true whether I'm in front of it. So in front of it, my right hand needs to curl in the direction to sort of point and my thumb points then into the screen, same thing, my thumb still points into the screen. In both cases, I get the same answer. So here, this curling right hand rule, so if we think about something like this, where it's going clockwise, here's 12, 3, 6, clockwise from our point of view. If we use our right hand rule, then looking at the screen, my hope is you take your fingers, you curl it like you're pushing the hand in that direction, and then your thumb points in the direction, so this would be into the screen. So that's the direction. And as long as we use our right hand, everything is going to be consistent. Because it turns out that if we have something that's rotating like this, and here's, let's do the one that we already did. Let's do V like this, so that would be our omega curling. This is clockwise, so our thumb into a screen, so omega is into the screen. In this case, we're going to say omega is into the screen. Omega into the screen from our curling right hand rule. If we do that, then we can say, in fact, that V is equal to omega cross R. Everything will be consistent. And so let's check this. R is in this direction. There's R. Omega is into the screen. It's a little hard to do, so we do omega is our first finger, R is our second finger. And so looking at the screen, my thumb is pointing down. So omega cross, omega into the screen, R that way. This is now down. I get a V is down. Okay, which is consistent with everything that I've seen. And what that allows me to do is anywhere along the circle, if I'm here, here, or here, using the same omega and the same R, I'll get the direction of V. And when the angle between R and omega, so the angle between R and omega is 90 degrees, then we get, which is the situation we're going to be working with the whole time in this course, you get V, the magnitude, is equal to omega times R, just like we saw before. So everything is all consistent. The last thing I want to say very quickly is about alpha, which is our acceleration. We have acceleration is dv dt. The Greek letter for the first letter in the alphabet is alpha, so that's d omega dt. So this is an angular acceleration. And it works the same way. We say that it is in the same direction as omega when we're speeding up, and opposite when slowing down.